Assalamualaikum and hi everyone. This is my third video on the respiratory system, and this time we'll be talking about gas transport in blood. Right, today we'll be learning about the transport of oxygen. So there are two ways that oxygens are being transported, and then as for carbon dioxide, there are three ways that carbon dioxide is being transported, and then we're going to look at hypoxia and cyanosis. So the transport of oxygen is mostly by hemoglobin. So I put here about 97% is transported in the blood. That's almost like all, right? And one hemoglobin contains four heme groups. We're going to talk about that later. And here I've put up a question: what about the rest of the oxygen? How are they being transported? It is through dissolved in the plasma, right? About 3% or a very little amount of oxygen is being transported this way by dissolving in the plasma. So these oxygen gases, they can dissolve, they can get dissolved in fluid, right? And we have the fluid part of the blood, plasma. So about 3% of this oxygen is being transported this way by dissolving, simply by dissolving in the plasma, and carried through the blood, follows the blood flow, and to its site where it is needed, it is being taken up by the cells. Okay, here is the hemoglobin molecule. It is made up of two alpha chains, two beta chains, and you can see that there's an ion group in the middle of each of this chain, and this is where oxygen is bound. So each oxygen molecule will bind to one ion group. So you have like one hemoglobin molecule can carry up to four oxygen molecules. Alright, now we're talking about the hemoglobin structure and production. And notice that I've put that in the fetus we have hemoglobin type F, where it contains two alpha chains and two gamma chains. And in adult we have hemoglobin A, two alpha chain and two beta chains, and that's about 95% of the hemoglobin is this type. And a small amount, a minority of it, we have hemoglobin type A2 with delta chain. So delta chain synthesis begins late in the third trimester, and in adults it has a normal range of about that 1.5% to 3.5%. So not much, but majority of the hemoglobin will be type A, because this is the most stable stable compound to carry oxygen. And we do have adults with hemoglobin F, and this is not normal, which is because hemoglobin F is not as efficient as hemoglobin A in carrying oxygen, but it has a higher affinity towards oxygen compared to hemoglobin A, which is why it is best in fetus, because fetus, you know that fetus has to fight over mother's oxygen. I wouldn't say it's like a fight, but you know, it has to be able to get oxygen. And you know that there's mother's blood as well inside, so there's and mother's blood also carries oxygen, and mother's blood has got hemoglobin A. And so by having hemoglobin F, which has higher affinity towards oxygen, then they have better chances of getting the oxygen, um, even though they are in the mother's womb. So that's why they have hemoglobin F. But in adults, you're not supposed to have hemoglobin F anymore, and you only have that in if you have sickle cell disease, or you have beta thalassemia, which is not normal, right? Okay, so this is the oxygen hemoglobin dissociation curve, and you can see that it is not a straight line. It's definitely not a straight line. It's got shape of like an S. And remember we talked about the partial pressure, and then it is denoted by the letter P. So you put PO2, it means the partial pressure or the pressure of the oxygen in the blood, right? So you have PO2 here, and you have hemoglobin saturation in percentage. And remember we've talked about the partial pressure of oxygen is within the range of 100 to about 40. That is what I asked you to memorize, right? And in some books they use 110, sometimes it can go up to 120. Most of the time you just have to remember it's from a range of 40 to 100, right? It can be less, it can be more than that, but 140 is good enough. Okay, so we have blood coming back from the lungs. Now remember that the lungs, they supply oxygen. So if they have just left the lung, it means that the oxygen is 100%, right? So you can see the top part of the graph here, 100% of the oxygen in the blood. So the blood has got oxygen. All of the hemoglobin are occupied, and all of its molecule or the chains are occupied with oxygen. And as it leaves the lung, okay, so slowly oxygen is being transported to tissues that are in need of oxygen, right? So you have the amount of oxygen reducing, and as you can see, the graph slowly comes down, right? As the partial pressure of oxygen reduces, it slowly comes down. It means this hemoglobin saturation of course comes down because more and more oxygen is being released to the tissues, and you have the partial pressure of oxygen also comes down, right? It means, yeah, it makes sense, right? But look at the amount of oxygen as it comes down when it reaches at about less than 60. So you can see that at first it slowly comes down, but as it reaches the partial pressure of 60, you can see here at this line 60, yep, at this line where there is partial pressure of oxygen here 60, right? You can see that it starts to drop even more faster, right? Look at this curve, it's even more steeper than the one that we've seen in the top part of the graph. What it means here is that the less as the partial pressure of oxygen reduces to 60, I mean if it starts to drop below 60, now the release of oxygen becomes more efficient, right? As one oxygen starts to diffuse out to the tissues in need of oxygen, you have more and more oxygen being released easily. So as one leaves, the other one becomes easier to leave. So you have more and more oxygen is being released. So you have a very fast release of oxygen now. So that's why you have a steeper curve of the graph here. And you can see that as the partial pressure of oxygen dropped to, now look at the partial pressure drop to about 40 here, right? You can see here. Now it is 40. And even more so, the partial pressure is now less than 40, coming down from partial pressure of oxygen 60 to now partial pressure of oxygen to 40, which is even less than the previous one, right? And you have limited oxygen is now bound to the hemoglobin. And uh, you see that the graph becomes really steep. What it means here is as your the partial pressure of oxygen drops to below 40, you have incredible amount of oxygen being released. Okay, so why is that less partial pressure of oxygen is in a state where you have where your body, it is in need of oxygen, where you have now when you're exercising, you have even more your tissues are even more in need of oxygen, so you have less partial pressure of oxygen, and therefore the release of oxygen becomes easier and easier, and that's why it's really steep. So what I'm telling you is that in a condition where your body has a lot of oxygen, where it doesn't need oxygen, it means that it has a higher partial pressure. You have slow release of oxygen because you don't need it, right? As the partial pressure of oxygen is getting less and less, particularly at 60 and below, you have incredible amount of oxygen being released from the hemoglobin. Okay, so it's kind of like efficient in a way. When you need oxygen, you have less partial pressure. Partial pressure of oxygen in your body is less, therefore you need oxygen, and therefore the release is fast. The release is faster compared to where the body is not that in need of oxygen, where you have higher partial pressure in the body. We have, for example, PO2 more than 60, right? 60, more than 60, then you have less of the oxygen is being relieved. You don't have that steep curve. Okay, so let's talk about the amount of oxygen carried by hemoglobin. So 100 ml of blood contains about 15 gram of hemoglobin, and each gram of hemoglobin can carry a maximum of 1.34 ml of oxygen. So in other words, 100 ml of blood can carry a maximum of 20 ml of oxygen, right? I mean, if you can do the math there, you can find that a 100 ml of blood carries about 20 ml of oxygen. So the quantity of oxygen released to systemic tissues, again, this is similar to the previous slide that I have mentioned, that the amount of oxygen is being released to the systemic tissues, depending on the partial pressure of the oxygen. For example, in a state where the partial pressure of oxygen is high, where you can see here, for example, in this area where there's high concentration of oxygen, so the partial pressure is high, so the rate of oxygen release is less. So you can see that the curve is not that bent, but you can see that there is reduction of oxygen concentration, but it's less. And then if you look at where the partial pressure of oxygen is decreased, look at when it reaches 40, especially because I mentioned that in my previous slide as well, that as the partial pressure of oxygen reduces, especially when it comes to partial pressure of oxygen level 40 and below, you can see that the amount of oxygen being released is much higher, at a higher rate compared to the previous graph, where you can see it's not so steep, but in this part of the graph is really steep, so the rate is really high. The release of oxygen is high. So here I've written down 100 ml of blood delivers about 5 ml of oxygen under normal circumstances. And then if, for example, we exercise and we are in need of more oxygen, therefore our partial pressure in our body gets decreased easily, for example, right? Because it's in a state where oxygen is being used up all the time, so you have the condition of the level of oxygen being reduced at a high rate, so you have that partial pressure is less and much less, and therefore the delivery of oxygen is at a much higher rate. So you have here 100 ml of blood can deliver up to 15 ml of oxygen during exercise, which is triple of the amount of oxygen being delivered compared to the normal one, right? In delivery during exercise, when we look at the rate of oxygen delivery, we say that during exercise, 100 ml of blood can deliver up to 15 ml of oxygen, which was in the previous slide, right? Remember? So the cardiac output increases up to 6 to 7 fold. Thus, by increasing oxygen transport and cardiac output, there can be a 20-fold increase in oxygen delivery to tissue during exercise. You can have up to 20-fold increase. This is important because during when your body is in need, you need to have the supply of oxygen, and the range is a lot. I mean, from normal up to 20-fold increase of oxygen delivery. That's a lot of difference, right? And then so it means that our body is capable of having that intense. You can have intense exercise, you can have whatever intense activity that you want to do. You don't have to worry, because our body is capable of increasing up to 20-fold of oxygen delivery. Right, so when we use the oxygen hemoglobin dissociation curve, what we want to look at is we want to look at the rate of how uh, how fast oxygen dissociate from the hemoglobin for it to be used by the cells. Okay, so again, I think I have mentioned this previously in the previous slide a couple of times, that the partial pressure of oxygen plays a big role here. So it depends on the surrounding. It depends on the environment. If, let's say, the blood leaving the lungs and it comes to an area where the partial pressure is quite high, right? For example, partial pressure is only about 104 millimeter mercury. So you have that hemoglobin saturation is at 97%. When we talk about hemoglobin saturation, we're talking about the concentration of oxygen inside the hemoglobin. The amount of oxygen being carried by hemoglobin at that time is about 97%. So there's only 3% less, 3% empty spots. That's what it means. Okay, so and what happened to hemoglobin saturation if there is a drop from 104 to 60 millimeter mercury? So let's say now the blood travels to an area where the tissue or the environment is at is at is having less oxygen, whereby the partial pressure of the oxygen is now 60 millimeter mercury. So now there is an an increased need of oxygen, right? So the hemoglobin saturation now drops to about 89%. So you can see that the difference in partial pressure from 104 to 60, so the difference is about 44. Okay, if you do the math, the difference is about 44 millimeter mercury. It's a big difference, right? But you look at the hemoglobin saturation, it drops to only about 89%, which means that the difference in the hemoglobin saturation is only about let's see, 97 minus 89, you've got about 8% difference. So 8% difference, meaning there's only 8% of oxygen being released, while the drop of the partial pressure of oxygen is from 104 to 60. It is about 44 millimeter mercury difference, which is that's how efficient our hemoglobin is. So it only supply the oxygen to, depending on the condition of the the surrounding tissue. If it's if it's in need of more oxygen, then it will be releasing more. But for now, it only drops to 60 millimeter mercury, and that's still okay. So the hemoglobin saturation only drops up to 89%. Now, if let's say the environment is in need of more oxygen, and the partial pressure of oxygen continues to drop below 60. Okay, for example, it drops down to 40. So if you look at the graph here, right, so if you look at the graph, as it drops below 40, this is 40, right? As it drops to below 40, 40 and below, meaning the amount of oxygen is low, right? So that's what it means by partial pressure 40 and below. So we are saying that the tissue are in need of more oxygen because it's now dropping 40 and below. So you can see that the graph now is really steep. Again, I mean I've mentioned before in the previous slide that the oxygen concentration and the rate of oxygen being released increases as the partial pressure of oxygen drops, especially from 40 and below. So now the rate of oxygen being delivered increases compared to in the previous um, um, in the previous partial pressure, where I mentioned when it drops only up to 60. You can see the graph is not that steep compared to the graph here. So the rate of oxygen release has increased depending on the demand of oxygen. That's what it means. Here is showing the oxygen hemoglobin dissociation curve, and I put here, you can see that on the left side, this one is increased affinity towards oxygen. When I say increased affinity towards oxygen, I'm talking about the hemoglobin affinity towards oxygen. So if and then if let's say all these things happen, this will cause the increased affinity of hemoglobin towards oxygen. And when there is these things happening, there will be a decreased in affinity of hemoglobin towards oxygen. And this is important because these are this characteristic of hemoglobin towards oxygen, it is really useful in a way that in your exercising, for example, you have an increase in temperature, and definitely you'll be producing more carbon dioxide, right? And then in a way, we're going to learn later that how increase in carbon dioxide can also cause a decrease in pH, making it more acidic. And then again, I will also explain about 2,3-DPG, but I'm putting it in here. So there is an increase in 2,3-DPG, also cause a decrease in affinity of hemoglobin towards oxygen. When hemoglobin has decreased affinity towards oxygen, it dissociate faster, it dissociate easier, meaning if hemoglobin has less affinity towards oxygen, it releases it easier. Okay, and if hemoglobin has increased affinity, if hemoglobin has a higher affinity towards oxygen, means it likes oxygen, therefore it will not be releasing it easily. That's what it means by increased affinity and decreased affinity. So in a condition when we look at a condition when we're exercising, when we need oxygen, we want to make sure that hemoglobin releases it easily, right? And so so this happens, when you exercise, this happens, right? So when this happens, it decreases the affinity, and when you decrease the affinity, the release of oxygen becomes easier, and therefore oxygen will be easily available for use when you're in need. That's what it means. And when you plot it, the values of the oxygen partial pressure and the hemoglobin saturation, just like when we did before in the previous slide, if you plot it, for example, in a condition where this is okay, this is a normal condition, and then you plot it again when you're exercising, or when you're in an area where it's cold and you're not exercising and all that. So you have different graphs. So you can see that the graph moves, the graph shifts to the right side if you're exercising. Okay, I'm gonna highlight this one here. So this is the right side, so it seems like the graph shifts to the right side. And if you plot a graph when you're not when you're not exercising, for example, when you're doing something that reduces the temperature and it reduces the partial pressure of carbon dioxide, and so on, and etc etc, you have the curve shifted to the left side. Okay, so this is what it is. Okay, now let's talk about the Bohr effect. When one molecule of carbon dioxide binds to hemoglobin, it causes the release of other oxygen molecules from hemoglobin. And what does this mean? It means is that when one molecule of carbon dioxide comes in and bind to the hemoglobin, it causes the release of other oxygen molecules from the hemoglobin much easier, and therefore oxygen can now be used by the by the tissues. Um, and the characteristic of the hemoglobin is that when carbon dioxide binds to it, somehow it changes its shape in a way that oxygen is being released easier and easier. So in a situation where there is in need of oxygen, for example in tissues where there's a lot of activity, I mean when you're doing exercise and all that, so oxygen is being consumed a lot at a faster rate, and more carbon dioxide is being released. And when hemoglobin fresh, the blood fresh from the lung comes in and full of oxygen, and carbon dioxide binds to the hemoglobin, it releases oxygen easier. Okay, because of the change in the shape of the hemoglobin inside the blood. And this is what we call as Bohr effect. Now let's talk about carbon dioxide transport. And before we moved on to carbon dioxide transport, I just want to remind you again that the oxygen transport has got two ways. How is it transported to the specific area in the body? Is the first of it is using dissolve, right? It dissolves itself in the plasma, which is the fluid part of the blood. And secondly, I told you that oxygen binds to the hemoglobin, and therefore it forms oxyhemoglobin, and that's how it's being transported. And majority, which is about 97% of the oxygen, is being transported using the hemoglobin method. Right, now let's look at the carbon dioxide transport. So it's it also is being transported through the plasma. It also dissolves in plasma. So I've shown here in the first part. Let me just use this one. So this is the first one, dissolved in plasma, right? So this is the first method. Carbon dioxide or any gases in particular, they can get dissolved in the plasma. Secondly, it can also bind in the blood. It can also bind with hemoglobin and form carbaminohemoglobin. So this is second method of carbon dioxide transport. So what's the third one? The third one is carbon dioxide can also be transported by forming bicarbonate. It can form bicarbonate, right? So through bicarbonate form, it is transported, I say, through the blood. Okay, right. So for example, if this is the cell tissue, right, first carbon dioxide from the cell tissue, and it is now entering the interstitial fluid and into the blood, right? So in the blood you have red blood cells and you have the plasma. So carbon dioxide combined with water, and then it becomes uh, carbonic acid, right? Carbonic acid, it dissociates. Carbonic acid is unstable and it can dissociate into bicarbonate and hydrogen ion here. So in the red blood cells, there's an enzyme called carbonic anhydrase, and this enzyme helps the reaction of carbonic acid. So when carbon dioxide combined with water, and it becomes carbonic acid, and the reaction is really fast with the help of an enzyme called carbonic anhydrase. And the again, like I said, carbonic acid is unstable and it will dissociate into bicarbonate and hydrogen ion here. So this again, carbonic anhydrase helps this reaction too. Okay, it helps the reaction of it from carbonic acid to dissociate into bicarbonate and hydrogen ion. So in other words, this bicarbonate will be from the red blood cells. It goes out from the red blood cells and into the plasma, right, through a chloride shift. Okay, so there's what it means is that for one chloride ion entering this red blood cell, you have one bicarbonate being released. And what about the proton? So hydrogen ion is also called the proton. So the hydrogen ion or the proton will combine with hemoglobin and becomes HHB. Right, so this is combined with hemoglobin, right? And this is how it is. So when it comes back to the lung, right, so the reaction reverse. So you have bicarbonate comes back in through the same chloride shift. Okay, comes back in through the same chloride shift, and then the chloride comes out, bicarbonate comes in, and then bicarbonate binds or combine with the proton, which is found from the which was attached to the hemoglobin. So now it is released, and now proton combines with bicarbonate and form the carbonic acid, right? So carbonic acid now dissociate, because it is unstable, dissociate into carbon dioxide and water, and therefore you have the carbon dioxide and water like before, and that's how carbon dioxide will then be released as you um, exhale out the air. So you have carbon dioxide being released. This is what happens in the lung, is the reverse of this, right? Right, so now let's talk about Haldane effect. And if you remember previously, we've talked about Bohr effect, and that Bohr effect is when one molecule of carbon dioxide comes in and attached to hemoglobin, you have release of oxygen easier. Okay, easier. Now Haldane effect is the opposite of that. So when one molecule of oxygen binds to the hemoglobin, it causes the release of other carbon dioxide molecules from the hemoglobin easier. This one is useful when the red blood cell comes into the lung area, right? When it comes into the lung, you know that lung has got lots and lots of oxygen molecules, and as one oxygen molecules comes in and bind to hemoglobin, so you have easy release of carbon dioxide, which was previously attached to the hemoglobin, and now it's released easily, and therefore after that you exhale and you remove the carbon dioxide out from your body. So in this way, Haldane effect takes place, compared to Bohr effect, which takes place when the red blood cells coming from the lung, and it comes to an area where there is in need of oxygen, for example in cell tissues. So that's when Bohr effect takes place, and in the lung it's Haldane effect, because the opposite occurs. Alright, so let's talk about now hypoxia. What does it mean by hypoxia? Hypoxia is a condition where there is less or no oxygen, right? So we have four different types of hypoxia. We have hypoxic hypoxia, anemic hypoxia, circulatory hypoxia, histotoxic hypoxia. And all these four types of hypoxia, I mean, they are all leading to hypoxia, a situation where there is not enough oxygen, but the types just tells you what causes the hypoxia. So now I'm not going to describe in detail to you. This is not going to be in your exam. I mean, for my students, what I want you to do is that I want you to look for this hypoxia, all those four different types of hypoxia, and then understand what are the causes of hypoxia based on the types, and maybe come back to me and tell me, or if you have any questions, or if you're not sure regarding any of the hypoxia, you can come and ask me. Okay, so this is the last part of my slide. It's good to know about cyanosis. Cyanosis is basically the bluish, skin due to deprivation of oxygen. And as you can see, there's a mnemonic for it called PALMS. And what you can do is that you can look through it and find out what causes the peripheral cyanosis and what causes uh, the central cyanosis, and differentiate it if you can, right? But basically this is all of it. We have covered the oxygen transport, and we have covered the carbon dioxide transport. So this will not be covered in your exam. Definitely not cyanosis, and definitely not hypoxia. I'll probably ask you more on the basic physiology processes, but definitely not this one. So if you have gone through my videos, you will hopefully be able to answer in the exam, because basically what I've asked in the exam questions, basically what I have explained in my videos. And so that's it for this video, and thank you for listening to me, and I'll look forward to our next and the last video for our respiratory system coming up soon, inshallah. Assalamualaikum, and have a nice day everyone. Bye.